let's start by trying to orthogonally diagonalize some smaller matrices. So this is going to be from 7.1, and we'll do 13 first. The third matrix is going to be 3, 1, 1, 3. And we know that we're going to be able to find some orthogonal basis of eigenvectors because this guy is symmetric. So how are we actually going to find those? Take a few minutes to give an attempt at that, and we'll go over it. So what's the first step going to be?
Would you try to find the eigenvalues?
Yeah. So we're going to find the eigenvalues, and how do we do that?
Determinant of the matrix minus lambda equals 0. And then
yeah. So we want this determinant, and what's that polynomial come out to?
Lambda squared minus 6 lambda minus 8.
We set that equal to 0.
Yeah.
And then that factors as lambda minus 2, lambda minus 4. So our eigenvalues are going to be 2 and 4. Did you find eigenvectors yet, or do you need time for that?
I found only one of them, but
Okay. Oh yeah, take a little bit to get the other one as well, and then we can go on from there.
What do we do after we find the eigenvectors?
So let's write out the eigenvectors that we have. So corresponding to 2, we have the matrix 1, 1, 1, 1. And we're trying to find the null space of that, right?
Yeah.
So what did you get for a basis for the null space?
I got -1, 1.
Right, so we have x plus y is equal to 0. So we have to have -1, 1. Then the other matrix is 1, -1, 1, 1, -1. And for this one, what did you get?
I got 1, 1.
Mm-hmm. So we know that these guys are linearly independent because they correspond to different eigenspaces, but are they orthogonal?
Yes, because their dot product is equal to 0.
Yeah. In this case, if you take this dot product, it's already 0, so we don't have to go through finding the projections and actually subtracting to get new orthogonal vectors, right?
Yeah. So in what case would we have to find? So if their dot product isn't 0, then we have to go find the projection?
Yeah. So it depends on the specific matrix. Some of them, like this one, the basis will actually just like actually orthogonal. But for other ones, you might have to do a little bit of work to find projections.
Okay.
Yeah.
So when we diagonalize, and so we just need to find the eigenvectors and that's it?
Yes. So first what we need to do is find the basis of eigenvectors, and then we diagonalize. And when we're trying to orthogonally diagonalize, all we're doing now is taking that basis and making sure it's also an orthonormal basis.
Oh, okay.
Yeah. So we start with this basis of keeping this order, yes. -1, 1, and 1, 1. And we want to get an orthonormal basis. They're already orthogonal, so we just have to normalize them, right?
Yeah.
And how do we do that?
Is normalizing them just making their magnitude equal 1?
Yeah.
Something like that.
So they're going to be unit vectors when their magnitude equals 1.
Yeah.
And how do we get vectors that are in the same direction as these, but with magnitude 1.
Wait, how to get them in the same direction?
Yeah, because if we like we want new vectors that span the same like we want the span of this like new normal this new unit vector, like say v, to be the same as the span of this vector, right?
Yeah.
We're trying to replace this with the unit vector. So which unit vector is going to do that?
I don't know.
So if we have like pictographically some vector out here, what we're looking for is, this is the, let me see if I can draw a nicer circle. Can't really, but if this is a unit circle, you're looking for this vector.
Oh, it's the vector divided by the magnitude, or
Yeah,
like square root
exactly.
of some sort. Yeah.
So it's going to be b over magnitude v. So take a quick second to compute that for each of these. And what did you find?
For the unit, or for the eigenvector -1, 1, I got -1 over rad 2, 1 over rad 2.
Yeah. And the second one's going to have the same magnitude.
Yeah.
Just that they're both positive.
Wait, can you re-explain why we said span? Oh, wait, never mind, I got it.
Oh,
So
yeah,
span of u is equal to the span just because there's u is just the, what's the term? Unit vector?
Yeah.
Okay.
There's the unit vector is pretty much like defined as the vector that has magnitude 1 that spans the same subspace, kind of.
Okay.
Yeah. And this is just the actual formula for how you find that.
Yeah.
So this is our new orthonormal basis. And then we still have to diagonalize it. Do you guys remember what we do for that? So we started.
Isn't it just like the eigenvalues? Oh, never mind.
So the eigenvalues are going to be part of one of these matrices, but so what does it mean to diagonalize something? If we're trying to diagonalize this, what types of matrices are we looking for?
Well, for this one, would it be a 2 by 1?
A 2 by 1 matrix?
Or I don't know. I don't know what you mean
vector.
by like what kind of matrix.
So what do we like when we say we want to diagonalize a matrix? What's like the answer going to look like? What's it asking us to do?
You're trying to find. I don't know.
Okay, so
Explain it.
the definition that we're looking for is that A is, diagonalizable if A is similar to a diagonal matrix. right?
Mm-hmm.
And what's similar mean?
Does that mean it can be simplified too?
Not simplified to, but it's going to be kind of like, intuitively you can think of it as representing the same transformation, but with some other basis.
Okay.
Wait, can you repeat that?
Yeah, so intuitively, what similar means is that it's the same transformation, but with respect to some other basis. And like what that means formulaically is that we have some invertible matrix P where it's A is equal to PD P inverse.
Oh yeah.
So what you're doing here is you're essentially going from your like standard basis to some other basis using P, then taking this transformation and then going back to the standard basis. Does that make
What would,
sense?
yeah, but what would P be in R? Like what?
So,
Yeah.
so essentially when we're diagonalizing, right, we have these eigenvectors V that form a basis, right? V1 and V2.
Yeah.
So let's call this B, for example, or maybe beta. So if we want to represent this transformation A with respect to our basis B, we're trying to find the images AV1 and AV2 as linear combinations of V1 and V2, right? Does that make sense so far?
Yeah.
And the nice thing about these vectors is that they're going to stay in the same subspace. And since they're eigenvectors, they're actually a scalar multiple of the vectors themselves. So AV1 is lambda times V1, or lambda 1 times V1. AV2 is lambda 2 times V2. So when we write these images with respect to our basis, what does this coordinate vector look like? So because AV1 is just lambda times V1, as a linear combination of V1 and V2, it's lambda 1 times V1 plus 0 times V2, right? So it'll be lambda 1, 0. Yeah. And similarly for the other vector. So we put that together and try to get this matrix. This transformation with respect to this basis is going to be diagonal with just the eigenvalues on the diagonal.
Okay.
So in our situation, where we have 3, 1, 1, 3. And what's this diagonal matrix going to look like?
That would be 2, 0, 0, 4.
Yep. And now all we need to do is change of basis. So this guy is in standard coordinates, right? So we know that this matrix has to go from B coordinates to standard coordinates. And then this matrix here has to go from standard coordinates to B coordinates. Do you guys remember which one is which?
I know one's the transpose of the other. Is
Not
that
quite.
true?
They're going
No.
to be inverses, not transposes.
Oh, yeah, that's what I meant.
So what does one of them look like? What's the easier one to find?
P.
Or like what's the matrix look like? The one that we find first usually. It'll be one of these two.
Oh, wouldn't the first matrix just be the eigenvectors we found? P?
Yeah. So this one is the one where the column vectors are the eigenvectors.
Yeah.
And does this go from standard coordinates to B coordinates or from B coordinates to standard coordinates?
This goes from B to standard?
Yeah, so this is the one on the left.
Why do we use this one instead of -1, 1, 1, 1?
Say it again.
Why do we use the unit vector version instead of the eigenvectors -1, 1, 1?
Oh, great. So what we're trying to do is orthogonally diagonalize this matrix, which means that this basis we use here isn't just any old basis, but it's an orthonormal basis.
Oh.
Yeah.
So it has to be normalized first.
Yeah.
Okay.
And then, did you guys find this or not actually compute it?
Isn't it?
Do you know? Oh, sorry.
No, no.
I was just gonna ask. Do you know for the midterm we're gonna have to compute the P inverse when we're decomposing?
Probably. I'm not sure what the format exactly will be. Usually, since I like do the 2x2 examples, the smaller ones, there's just a formula for them. So that formula is like handy to have. For larger matrices, there's actually like more work involved. So it depends on whether it's going to be like a smaller problem or a longer, more involved problem.
Right.
Yeah, I think for 2x2s, you should know the formula.
Yeah.
But I always mix up the signs.
Isn't it you flip? So like say if the matrix is A, B, C, D, you'd flip B and C and then switch the signs of A and D.
Flip
I don't know if that's true.
B and C, and then flip the signs of A and D.
Or A, I don't know.
I
Maybe.
think it's the other way.
Or the other way.
Okay, so then
You flip B and C signs and then you swap A and D.
Okay.
so is that what we'd get? I think you have to divide by something too, but it's
determinant.
going to
Yeah.
be 1 here, right?
Yeah.
Because it's 1/2 plus 1/2. So I think that's what you get. Cool. So then this is our orthogonal diagonalization questions. Okay, let's see. Is there questions from earlier homeworks that you want me to go over that I skipped? Or continue on with this stuff? Because I think for last week's homework, it was all like very computational problems, since a lot of the conceptual ones were assigned.
We can just continue like this. I feel like it's a good review.
Okay, cool. I like this problem. So show that if A is an n by n symmetric matrix, then it's ax dot y is equal to x dot ay. So see if you can come with a good approach for this proof. Do you guys get it, or do you need a little bit more time?
I used a method, but I'm not sure if it's right.
Okay, let's give it a shot. So how'd you start?
So since it's symmetric, that means that it can be that A equals PDP inverse.
Equals PDP inverse.
And then in the equation ax dot y, I replaced A with PDP inverse and then parentheses x, and then y on the outside.
So
Isn't that for similar matrices?
um,
Or how do we know that is some
so
like
if
diagonal?
A is symmetric, the spectral theorem tells
Oh,
us
actually-
that's going to be
Yeah, that's my bad.
diagonalizable. Yeah, you can always write this for a symmetric A.
Okay.
Yeah, so like the big theorem of this chapter is that if A is symmetric, you get essentially a bunch of free properties all at once. We have, let me make sure I don't skip any of them. So you have symmetric and n by n. You're going to have n eigenvalues that are distinct and real, right? Or
Which chapter is this?
This is 7.1.
Oh, okay.
Yeah. Actually, I'm not sure if they're always distinct. You have and eigenvalues, counting multiplicities that are all real. So that means that our characteristic polynomial will actually split. We have n roots of it, counting multiplicities, yeah. And then beyond that, we also have that the algebraic multiplicity is equal to the geometric multiplicity of each eigenvalue as well. And what does that mean for these eigenvalues? If we have some number of eigenvalues, but the geometric multiplicities all are actually equal to the algebraic multiplicities, what can we say about all these eigenspaces?
Are you saying like it's diagonalizable, or is that like the part 2 of what you're saying?
So yes, it's diagonalizable because all these eigenvectors are going to form a basis. Right? Remember that in the case where A isn't necessarily symmetric, right? We can have the geometric, let me just read it as GM. The geometric multiplicity is less than or equal to the algebraic multiplicity. And if it's strictly less than, then you don't have a basis because your eigenspace is too small. Right? So when these are actually equal, then your eigenspaces are large enough that each of them, you can take a vector from each of them and get a basis for all of Rn. And not only do we have the basis, but the basis is, going to consist of, what's the most precise way to say this? Again, vectors from different eigenspaces are orthogonal, right? If we, like, let's say we had some actually questions about these first before I explain the significance of that. Okay, cool. So if we had some, say, like let's say A wasn't symmetric and we had some eigenspaces that form some basis, right? So let's just say like we have like some matrix where we have the x-axis as an eigenspace, and then this line y equals x as an eigenspace, right? So then what we get is we get this basis consisting of these two vectors for Rn. Now, given any basis, we can do gradient transform again, orthogonal basis, right? And you get something like the standard basis here, right? But the key thing is that when you do this, there's no guarantee that this new vector you find is an eigenvector of your matrix. So this vector here now isn't an eigenvector of our transformation. So that means that we can't diagonalize it with respect to this basis. The only basis we can use to diagonalize is this one here. And sure, you can like normalize the vectors, but you won't get an orthonormal basis because these vectors aren't orthogonal. When we have a symmetric matrix, this theorem is saying that in fact, your eigenspaces will never look like this. The eigenspaces for different eigenvalues will actually be orthogonal. So you don't have to do Greenwich on different eigenvectors to get this orthonormal basis. You get an orthonormal basis of eigenvectors for free, essentially. And if the eigenvectors for an orthonormal basis, then we can do this diagonalization and get, and we can say it's orthogonally diagonalizable. Orthogonally diagonalizable. Right. Questions about that?
What's the significance again of it being an orthonormal basis?
Like, why do we care about this basis being orthonormal?
In order for A to be orthogonally diagonalizable, we have to have an orthonormal basis.
Yeah, so an orthonormal basis of eigenvectors, right? Here, I just went through an example where like, this is like the eigenspaces of some other matrix B, which isn't symmetric. And because this basis of eigenvectors isn't orthogonal, if you use this basis to diagonalize it, of course, you're not going to get an orthonormal basis because these vectors aren't orthonormal, right? So this PDP doesn't work for this choice of vectors. If instead you find some orthonormal vectors from these, right? Given this basis, we can always find an orthonormal basis, right?
And sorry, this might be a dumb question. I just don't remember. What does orthonormal mean geometrically?
Geometrically, it means that they're perpendicular and also unit vectors. So a basis of like, say, like that's one example. Something like that is another example.
Mm-hmm.
Yeah.
Okay, I get it. Thank you.
Mm-hmm. So other questions about this? If you're asking like why do we care about orthonormal be something orthogonally diagonalizable anyways, like this property is actually really useful in a lot of other areas of math and physics. And it's like one of the reasons we have this theory of symmetric matrices to be able to manipulate dot products like this. Other questions about this theorem, the spectral theorem? Let me make a note here. Sometimes you do have to be careful when your eigenspaces have more than one dimension. So there, if you have like, let's say you have a three-dimensional matrix, and if one of your eigenspaces is two-dimensional and the other isn't, different vectors from different eigenspaces are orthogonal. But not necessarily ones from the same space. So if you're not careful, you could accidentally pick eigenvectors which are linear like if you have two orthogonal eigenvectors, you could accidentally use a basis vector that's a linear combination of those two, and you don't want to do that. So that's something you have to watch out for. All right, back to question 27. So we had A is equal to PDP inverse, and then we wrote PDP inverse dot x. And then what was the next step?
And then the y would still be on the outside since it's being multiplied.
Oh wait, this is yeah, you're right. I wrote this wrong. This isn't dot x. This guy is multiplying x, and then we have dot y on the outside. All right.
Then could you distribute each of the matrices in the PDP inverse to x?
What do you mean distribute?
Like, I'm not sure, is this P inverse times x, or is this the entirety of PDP inverse times x?
So this will be all of PDP inverse times x. But you could
So-
like write it as PD times P inverse x. I'm not sure if that helps you too much with this problem. I think there might be a way to do it using this, but it might be a little bit more involved. You might need some other properties. Okay. So let me give you guys a hint that will make this a little bit more straightforward. So do you remember how to actually compute the dot product?
X transpose Y.
Yeah. So try using that.
Wait, you don't need to use the A equals PDP inverse to do this, right? Or
No,
like is
I don't think so. I'm sure that you
Okay.
could reason with that form, but it's a little bit
Okay.
more of a messy expression. I haven't thought through what the answer might look like.
If that's the case, then can't you just do AX, like that entire parentheses transpose dot Y is equal to A transpose X transpose dot Y?
A transpose, X transpose. So remember when we take the transpose or inverse of a product of things, what do we have to do?
Oh, flip them.
Yeah, you have to switch the order. The
Yeah, so it's X transpose.
stocks
Yeah,
and
yeah.
shoes principle. And then what's next?
And then X transpose is equal to just X.
X
Right.
transpose is equal to X. X is going to be a column vector, right? So X as a column vector is not necessarily the same as a row vector.
Yeah.
Because if we
Oh,
have
but we
like
can
two
say
column
X.
vectors, we can't. Oh yeah, go on.
Yeah.
We can
We
say
can
what?
say X transpose times Y is equal to X dot Y. Right?
So that's
Can we
true,
not switch those around?
but not necessarily, no.
Oh, okay.
But what do we start with A being here? What was the assumption that we made?
Oh, it's a square matrix.
Not just square, but it's,
Oh, symmetric.
yeah. So we can replace this A transpose with A,
Okay. Yeah.
since A is symmetric, A is equal to its transpose.
Hmm.
And then it's just rewriting this.
Right. Okay.
Cool. Everyone got that?
What happened to the transpose on the x in the third step?
Oh, whoops, that should have stayed there. My bad.
Okay.
Cool. So I think this is like, I don't know how much will come up in this course, but it's like generally the reason we care about these two types of matrices, orthogonal matrices and symmetric matrices, is that they work very nicely with this dot product we've defined. With orthogonal matrices, if we have some dot product, this orthogonal matrix preserves that dot product now. So applying this transformation to both of them isn't going to change this value. And that also means that it preserves magnitudes. So this kind of very like neatly classifies what type of matrices are going to be orthogonal. On the other hand, symmetric matrices are a bit more abstract. What now this is saying is that it plays nicely in the sense that we can kind of interchange which vector we're taking, which vector we're multiplying by a when we're taking this dot product. All the matrices, they have this, it's not super hard to find this relation where like for two other matrices, you'll have something like this, where these matrices kind of like correspond to each other. But the nice thing about symmetric matrices is this dot product relation is preserved by itself. So A can act on either X or Y, and it doesn't matter which one it's acting on. Any other questions? Cool. We can go over SVD on Monday then.
Okay, thank you.
Cool. Yeah. Have a good weekend.
Thanks. You too.